Hello everyone, I am Dr. Ganesh Patil, working as Assistant Professor in Physics at SNJB ACS College, Sandwad. In this lecture, we are going to discuss about the thin films, how it is helping for doing the surface modification of particular materials. So, here first, before going to start, let us know that what is the definition of thin films. So, at the onset, let me discuss that thin film is very difficult to define because some people think that 300 nanometer is the thin, some people are thinking at 2 nanometer is also thin. So, the thing is that its dependence upon the application, that whatever the application of that particular material, based on that we can define that material whether it is thin or maybe the thick, because I will give some examples where you can find that in nanometer also there in some kind of materials which can act as a thick. So, thin film is a layer of substance or material on supporting substrate ranging from nanometers to several micrometers in thickness. As I already told, maybe that size may be nanometer range, maybe sometimes it is in the micrometer range also. So, thin film or maybe the thick film, the limit between thin and thick films cannot generally be defined because it is very difficult to say. Although literature sometimes gives an arbitrary value of 1 micrometer, basically a film can be considered as thin when its properties are significantly different from the bulk, because when we are making that thin film that is giving the better properties in terms of electrical, in terms of mechanical, in terms of thermal than the bulk or maybe the thick film. So, for example, an indium oxide film which can be used as temperature barrier. This one is the material coating due to its high transmission in the visible range and its high reflectivity in the infrared region. This is caused by optical interference effect, has to be approximately 300 nanometer thick. So, you can imagine that here 300 nanometer we are considering as a thin materials. For optical applications, thin film can be considered as thin, but when we are talking about particular this application, that 300 nanometer we are considering as a thin material. If the same material would serve as insulator in a Josephson junction, 300 nanometer would be much too thick to allow Cooper pairs. Cooper pairs is not nothing but the material which we are using the in between the two semiconducting layers. So, through the oxide for this application, that indium oxide film should have a thickness of only 2 nanometer. So, now my one big question is that whether we are going to say that 2 nanometer as a thin or thick, or maybe by which one is thicker or maybe which is the thinner, whether 300 nanometer or maybe the 2 nanometer, here are the answers. In other words, for one given application as thin film can be considered as the thin, while another application as the same film can be knowing as a thick. So, it depends upon application to applications. Somehow, somewhere one film can be used as a thick, somehow the same dimensions can be used as a thin films. So, in this slide, we can see the classification of thin films on the basis of crystalline structures. So, it has a or we can divide the thin films into 4 classical divisions. One is called single crystal, another one is epidaxial, another one is amorphous, and the last one is polycrystalline. So, in this particular slide we can see the effect of thin films. So, just in this particular slide I am going to discuss about if you are going to use those kinds of thin films, what are the advantages we are going to get. So, the microstructure which is different from the bulk, that means in respect to grain, crystallite size, the following effects may be observed: increase corrosion resistance, to improve hardness, to enhance magnetic saturation induction, which is nothing but we are going to getting from this particular slide. It is the saturation magnetization which is on the x axis, and the x axis is giving the temperature. So, from this particular case you can see that when our thin film thickness is only around 2.1 nanometer, it is giving the absorption magnetization values at around 600. So when we are using our material as a thin, that property is getting increased. So what is doing it is in increasing corrosion resistance to improve hardness, increase critical temperature of superconductivity, amplify the optical absorption. So if we use the thin film, then it can enhance so many properties than the thick film itself. So in this slide we can see how we are doing this thin film, or maybe rather we can say how we are preparing these thin films, what is the growth mechanism over there. The deposition process of a film can be divided into three basic phases. So first one is called production of the appropriate atomic, molecular or ionic species. So this one is the number one method. Then second one is that transport of these species to the substrate through a medium. So this is the second one. And last one is that the condensation on the substrate, either directly biochemical or electrochemical reaction, to form a solid deposit over there. So here this is the gas flow is going on. Then the atoms is coming first, abruption on the film is taking place, then nucleation of this atom is taking place, and the last one is that step flow growth, means layer by layer it is forming, and it is giving a coating on the material surface. So in this particular slide we can see a particular motives of thin film depositions. What are the logic that why we are going to use this kind of thin films for surface engineering? So first is that to maintain the surface uniformity. So we can get a homogeneous surface over there, smoothness of the surface will be good. To reduce the amount or mass of light observing materials, to decrease the weight and bulkiness of the material. That means we are reducing the weight, we are reducing the volume, but simultaneously we are ensuring the properties than the bulk film or the thick films. Growth of thin film generally exhibit following features, that is the origin of thin of the materials created by any deposition technique starts with the random nucleation process, followed by nucleation and growth stages. Nucleation and growth stages are dependent upon various deposition conditions like growth temperature, growth rate, or sometimes substrate chemistry. So the thing is that it depends upon recommended that how many layer we are going to make to the substrate, what is the substrate condition, how much temperature can sustain this substrate and the thin films. So it depends upon what property you are going to achieve. So depending upon that, we can go for a single layer, we can go for a multiple layer deposition onto our substrates. So basically the different kinds of or different techniques of different so in this particular slide we are going to discuss the different techniques of deposition on thin films. Generally it can be divided into two parts. One is called the gas phase and the other one is called the liquid phase. Gas phase, generally we have discussing about the PVD process, that is physical vapor deposition process, and the CVD we can call it as chemical vapor deposition process. And we can see these different techniques in the next lecture. Thank you.